All right, this is the second day video for doing calculus with parametric equations. The first day was really long and we covered a lot of information in there. This one will be shorter. In fact, it's so short with just really one example. I'm going to go through the derivation for the formula. So another thing we can do, one of the main things we do is what we covered yesterday, using the derivatives of dy dt and dx dt to form the derivative dy dx, and then treating that as a slope, and analyzing things like slope and concavity and making tangent lines. The second part here, we're going to talk about what's called arc length, finding the length along a parametric equation's path. Right, so we already have a function for finding arc length that we found earlier in the course, and it was this function here, which is that the arc length is an integral from and the integrand is the square root of 1 plus the derivative of the function squared, and then you integrate over x from some starting to ending value. And that gave me, for a standard function where y here is a function of x, it gives me a way to find the length along the path. Okay, but we also know that this derivative f prime of x, that is the slope of a curve at a particular x. So it should represent dy dx. But now with parametric equations, we have this third variable dt, or t, and we know that this dy dx is equal to dy dt over dt dx. So if you plug this expression, dy dt over dx dt, in for the f prime of x, you can do some kind of fancy algebra here to drive another equation for arc length. So this is the arc length equation when we're using what we call rectangular or standard functions. Okay, rectangular, sorry, that should be rectangular or standard functions. Okay, but we're going to drive an alternate equation that we can use when we have a curve expressed in parametric form. So if we plug this in for f prime of x, first we can get a common denominator by making this 1 dx squared, dx dt squared over dx dt squared, so we have a common denominator. And then we can take this, remove this common denominator to the side to be 1 over dx dt squared, leaving dx dt squared plus dy dt squared. And then we can separate this into its own square root so that we can undo this square and write this as 1 over dx dt. But 1 over dx dt is dt over dx, which means the dx's can cancel out and just form a dt. And that gives me a new integrand, but we've changed the variable integration to dt. It's simply that the arc length is the derivative dx dt squared plus the derivative dy dt squared under the square root, and then we integrate that over dt. So we have this arc length equation that we can use for standard forms where the radical is 1 plus f prime of x squared integrating over dx, or if we have parametric form, we can take the integral of the square root of dx dt squared plus dy dt squared and then integrate over dt. Right? So why would we want this other form? Well, the differences are this. In the original form we had, we only had y as a function of x, right? So this is y is a function of x, right? And that means the domain is x, the x variable itself. So this dx represents a little piece of the x-axis. And then what's happening when we multiply by this radical is it's changing that into a little curved piece along the parameter. In Calc 3, we call that ds. It's a little distance along the curve, right? And then what we're doing with the integral is we're integrating a whole bunch of those little pieces to form the length, the arc length itself. But we're integrating along the x-axis itself. So now what we're doing is we're saying x and y are both functions of this new variable t. Maybe it's time. Let's call it time. So this dt represents a little change in time. By multiplying by the square root of the sum of the squares of the individual derivatives, we're taking that little change in time and changing it into a little change in length along the path. And then we're integrating up all those little paths to find the total arc length. Right? So it's a different way of thinking. We're integrating over a variable that's not actually a length on the graph. But by integrating over that, we've got these two equations whose derivatives translate that into change in x and y. Right, so why is that really good? Well, there's a couple big changes. the new expression has two advantages. The first one is the original equation for arc length can only be used with functions, right? So you cannot use that for some situation like this because this is not a function. It fails the vertical line test, right? So the new function, the new arc length equation can be used for non-functional curves. And the second thing is, in next year in Calc 3, we can easily extend this into 3 dimensions by just adding another term for the z direction so that x, y, and z are all in terms of t. And that means we can have what we call space curves that curve around in 3D space. And we can use this equation to find the lengths of paths in 3D space instead of just 2-dimensional space, right? So really, really a lot more flexible definition, right? But the nice thing is it's very easy to use and a lot easier than the previous example. So I just have a single example here because there's not very many ways this can go. Let's say that we're saying find the arc length of a curve that's defined by x is parametric equation is 6t squared and y is 2t cubed, and we want to find the length of the arc from 1 to 4. Okay, so we'll simply say the arc length is equal to an integral from a to b, this is the pattern for it, of the square root of dx dt squared plus dy dt squared dt. Right, so to fill this in, we're going to integrate from 1 to 4. We're going to take the square root, and in this I'm going to put the derivative for the dx dt. So that derivative would be 12t squared plus the derivative here is going to be 6t squared squared. And then we could just integrate that. Let's actually just go ahead and do that in a calculator with our Math 9 function. So I'm going to put this into functional mode real quickly. If I go Math 9 and I do an integral from 1 to 4 of the square root of parentheses 12t, that's going to show up as an x, but that's that squared, and then plus parentheses 6t squared, close those parentheses, and then square that dy dt, and integrate that over the variable. I'm going to get a number that represents the length. So this is 156.525. 156.525. 156.525. All right, and that's the answer. This is the setup that produces that. All right. Now, we could, let's just graph it real quick and see what this curve looks like. Since this is the only example, the video is pretty short. What if I were to go to parametric mode and graph this function? So that means we clear out what's there. This is x is 6t squared, and y is, I don't think this is going to be a very interesting looking graph, t cubed, but let's go ahead and graph it. If I go from zoom 6, that's origin plus or minus 10, it's going off really quickly. If I want the parameter to be from 1 to 4, I can do that. I think, let's see, if I plugged a 4 in here, this would be 4 cubed. 4 times 4 is 16 times 4 is 64 times 2 is 128. So we have some really large distances here. Let's have x and y go, let's go from like negative 130 to 130. That way we can kind of get something that's square and you can see what's going on. Negative 130 to 130. I graph that. All right, so it's not a very interesting graph, but this is the parametric graph, and 156.526 is the length along that graph from t equals 1 to t equals 4. All right, and that's really all there is to it. So this should be the easiest problems on the test would be arc length. But we do have to memorize these functions. All right.